Okay, we're going to quickly go into parametric equations. The reason parametric equations are called that is they take something called a parameter. That's a variable that will use another variable that controls how each function works. So a parametric equation to draw a graph has two components. We have the x component and the y component. The control can have a limited domain and range. We need to be able to find the domain and range of these functions, and in some cases find the Cartesian equation that is equivalent to them. So I'm going to do a couple of quick examples through using stuff from the book. So the first part is this whole thing about a parametric equation. We have two equations that create a point. And as you change the value of t, the point moves. So if I increase t, you'll find both graphs are moving up. And we go up, and A keeps going up depending on the value. The way you could calculate them is by putting in values for t, and that would allow you to draw the point. So you could take your calculator, use the table function, and calculate certain table values. So for quick plots, give me the graph. So to plot, what we can do is we can choose values of the t, the value of x, the value of y, and it gives us coordinates. So if I put t equals 1, 1 squared plus 1 is 2, over 1 is 2, and we get 2. That gives us a 0.22 that you can see here on the graph. When I put in the value 2, I'll just change the way the graph points and we can just calculate. I'll assume you'll try. So I've just turned on the coordinates of this point. So from when t is 1, we get 2, 2. When I change t to 2, we get 2.5 and 4. So we can actually plot our graph with some accuracy. So we start off with 2, 2. We've now got 2.5 and 4. Go on, calculate again. So if I put in 3, and 3 leads to 3 and 1/3, and 6, 3 and 1/3 and 6, and that's moving off quite nicely up that way. Let's come backwards, find 0. And what you'll find on your calculator is when you do 0, it gives error for x and 0 for y. And that's all the way off over here on the right hand side of this graph. The error is actually an infinity. So that's not very good to us for finding the graph. So what you then do is you go back into your calculator and you change the step so the numbers are smaller, and maybe do them as 0.2s. So let's go up at 0.2, and we then fill in the gaps in between. So we get 5.2 and 0.4. 3, 4, 5.2 and 0.4. Go to 0.4, and you get 2.9 and 0.8. So these numbers are what you would get from putting this into your calculator. 2.9 and 0.8. Let's go up to 0.6. 0.6 would give me 2.26 recurring and 1.2. 2.26 recurring and 1.2 is a point up here. 0.8 is going to give me somewhere very close to the point we've already got. 2.05 and 1.6. 2.05 and 1.6. And now we're getting the shape coming through that we've seen on the graph already. 1.2 maybe, and that gives me 2.03. This time the other side, it's actually going the other way, 2.4. So 2.03 and 2.4 is about here. And I've now filled in enough information that I know the shape of the graph. Y, x, 2, 2, 0. Okay, so we can now draw the graph in using that. The next part we need to be able to do is find the domain and range for this function. So I'll just take a copy of the curve, the information above. You can see it from the graph, but we'll go through it logically. Come on. So now if we want the domain, range, let's do the domain first. Things to consider are what values of t, first of all, are limits, and what sort of limits are they? So this said t must be greater than 0. So if we say t equals 0, the coordinates we're getting, the x value, is not part of my domain. But it gives us the boundary. So when t equals 0, let's put it in, find out what it says. We know from the graph what happens. X of 0 is 0 squared plus 1 all over 0, which is infinite. So we know it goes up to infinity on positive value. As we say t goes to large, the limit as t goes large, we might want to change the form of this equation and think this is also t plus 1 over t. And when we get to large t's, the t get big, very big, plus a very small value. So this actually leads to limit as x as t goes to infinity. The limit of this x is infinity plus 1 over infinity, again goes to infinity. So we know there is no upper limit. So we're now left with a point. We've tried limits. What about finding a local limit? So a local min or max. And we need to try that. So we'll do the differentiation of this function. So we now want to do the dx dt in the domain dx direction. So we want the dx dt of t plus 1 over t. Don't get excited. This is not anything going to be anything to do with logarithms. Remember, it's a t to the minus 1. So we get differentiate t, and we get 1, and we get plus what that is, sorry, minus that, because it's a negative 1. Take the old power, multiply by the old power, minus 1. Come on, give me the pound sign. And decrease the power by 1. Now this is actually a bit of a proof. We now make an assumption, assume there is a min. So we're going to say this equals 0. So let's put that in. 0 equals 1 minus 1 over t squared. Rearrange it and we get 1 over t squared equals 1, which also leads to t equals plus or minus 1. Now you might sit there and go, oh, hang on, what's going on with this? Well, the first part is we need to consider only t is greater than 0. So we've got t equals 1, t equals minus 1, t is greater than 0, so we don't worry about that piece. So we now have a point when t equals 1. 1 is not my minimum value though. Remember, this tells you what happened to t. So we now put in x equals 1, and we've already done that in the table above, so it is 1 squared plus 1 all over 1, which is 2. And that tells me the domain for this function is 2 is on the small side of x. Am I allowed to have the t equals 1? Yes, so it is less than or equal to, and then x can continue up to infinity, or x is greater than or equal to 0. The range for this, let's pull down that and bring down the notes. Let's do the range for it. So the range part. Now we're trying to find out what happens to y. So do the same thing. What's the limit when t equals 0? Boundary, not the actual limit. Y equals 0. That tells us we're not actually going to be at 0 unless it comes up in any other way. So greater than that one. Limit as t goes to infinity of y. So this goes up, so y goes to infinity. Again, nothing telling us which value is going on. So let's do dy dt, a local value, and that tells me that that value is equal to 2. We're going to assume there is a minimum. And if we assume the minimum, we're going to say that the 2 must equal 0. Well, there's a contradiction. So we've just done a proof by contradiction that tells us there is no local minimum. So that means that my range is purely governed by these values here, and this says that we don't go to 0, but we can get to things going up to infinity, and it's positive infinity. So y is greater than 0, and it can't be equal to, because this 0 only comes when t equals 0. Okay, it's not like the log ones. Notice as I increase, the y is increasing. Okay, so it's not that close to.